friends, I have delivered a good number of lectures on energy and environment related issues of general interest and also of specific interest as regards non-ferrous metals production is concerned. I will deliver one more lecture, and that will be the end of this module number 9, and that actually would formally end all the lectures I had to deliver for the course. But before I begin this last lecture, I would like to point out some mistakes that were there in a table I showed last time. Remember that I showed a table where I compared process energy and free energy for the production of various metals. I was trying to show that the actual energy you need in a process is much more than the free energy of formation of the compound, and the reasons are obvious. If we had the pure compound with us, we will need as much energy to decompose as the energy that was required for formation. But we need much more, because very often we start with a low grade ore, we go through concentration steps, we do many more things before we come to the final product from which we are to produce the metallic value. Now, the table I had shown had figures all jumbled up, and you have to ignore that table. I cannot delete it from the recordings, because that has already been recorded. Please look at this table, which makes things simpler. Here, these are the products that we are producing in an industry, and I am showing here energy requirements for production of metals from their concentrates and comparing with free energy. Actually, I am leaving aside some very preliminary steps of mining, etc. We are just starting from the concentrate. You see, the free energy for titanium dioxide will be only 4.0, but to make the titanium sponge, we will need so much more energy. Similarly, for magnesium, almost 16 times, aluminum ingot, see process energy and theoretical energy that should decompose the mineral. Look at ferrochrome low carbon, sodium metal, nickel cathode, ferrochrome high carbon, ferromanganese arc furnace, copper refined. Wherever there is an electrochemical step coming, you will find there will be difference between this and this will be more, etc., etc. Only in the case of tin and lead, we find that the difference is not so much, because one does not need that much of energy to decompose to get lead or tin or steel from the concentrates. But the last column is significant. The process efficiencies as defined in terms of these two are very low in case of titanium sponge, magnesium, aluminum, ferroalloys like this, nickel cathode. It is slightly higher in the case of steel and tin. So, you get the idea that we have to spend energy in the initial steps before we come to decomposition. And this is what I said, that considerable gap exists between the theoretical energy required for extracting a metal from its mineral and the actual energy required for winning it from its available ores. This is because ores and minerals contain a lot of gangue, which consumes considerable energy during processing. With the many unit operations involved in minerals and metal processing industries, several of which require significant inputs of energy, this industry has experienced substantial increase in percentage of total cost of energy alone. And I had earlier mentioned that in the case of aluminum, 40% of the cost of the metal or even more is only the price of energy that has been used in the production of the metal. Energy consumption, energy distribution, for the that consumed for copper production I have shown. And again I want to emphasize that crushing and grinding takes enormous amount of energy, 73.5% of the energy is going into crushing and grinding, little less for flotation and filtration. And so, whenever there is a crushing or grinding involved, you have to be very cautious. Now, there are several approaches to energy saving, and again this is a kind of repetition of what I had said. Through control, through optimization, through grinding aids, we can save energy. Similarly, through flotation cell enlargement, if you have larger flotation cells, then also will cut down on energy consumption during flotation. There is lot of energy required in drying whenever we have wet solids, and there are now newer drying techniques, newer methods of dewatering. These are all advances in technologies, and some of them have been listed. Now, since I mentioned the subject of grinding, which consumes enormous amount of energy, crushing and grinding has become very important disciplines for research. To design new kind of crushers and grinders which will take less energy, then there are grinding and crushing circuits, means instead of taking the material and trying to grind it all the way to a finer sizes, there are now techniques that you partially do crushing, partial grinding, take different fractions, do them separately, again mix them in intermediate, all kinds of combinations, and these are called the comminution circuits. They have all been done. The whole idea is overall, when you go from larger size particles to very fine size particles, we should not use excessive energy, or at least we should use as low an energy as possible. Now, to what extent this subject is important would be clear by the first statement, that size reduction in mineral industries accounts for about 3% of the total world electrical energy consumption. Total world's electrical energy consumption is so high, 3% of that is only being used in crushing and grinding of minerals, and it is estimated that the energy consumption in comminution, it should be comminution, constitutes over 50% of that used in raw material processing. It has also been estimated that grinding process efficiency is generally only 1.5 to 12%, means the rest of the energy is wasted as heat, and the majority of comminution tasks being carried out at less than 5% efficiency. Sustained research carried out over last 3 decades indicate that scope for improving energy efficiency of traditional grinding machines such as ball mills is limited. In a ball mill is a ball mill, its efficiency cannot be improved so much. It has been estimated that the potential energy saving with existing technology is about 13%, compared with 29% energy saving through improved or new technology. And one new technology is called high pressure grinding, where during grinding very high pressure is applied from both sides onto the particles being crushed or ground. There are also ultrasonic grinding mills, where ultrasonic sound waves are used. There are stirred mills, and comparison with conventional ball milling for grinding of limestone, cement, clinker and coal indicates that in all cases the new grinding devices gives lower specific energy consumption with possible energy saving of 15 to 40%. A substantial amount of energy can be saved during grinding if you use newer grinding techniques. Of course, it will depend on the grinding unit selected and the time of material being ground, obviously. Now, the energy saving potential when one uses this high pressure grinding rolls. I do not think I have a picture of that, but essentially, whenever crushing or grinding is done, there are two rolls through which the material to be crushed or grinding has to be passed. Generally, the crushers are fixed, but in this case the crushers press onto the particles which are going through the space where they are being ground. That is why, and they are under high pressure. So, they will be called high pressure grinding rolls. Now, this is the kind of energy saving that people have claimed. We can save 15% in copper ore grinding, 45% in the case of nickel ore, 26% in another kind of copper ore, granite 23, bauxite 41, clinker 32, gold oxide ores, gold sulphide ores containing gold, limestone 57%. So, this is on the basis of energy consumption recorded using high pressure grinding rolls in these units and energy consumption predicted using Bond formula. One can calculate the theoretical energy requirements for crushing. So, the summon substances, high pressure grinding rolls and other techniques must be used. To go back a little, we will come back to the subject again. Where is all this energy coming for non-ferrous extractive metallurgy or other industries? Since we are talking about non-ferrous extractive metallurgy, talk about aluminum, which consumes the maximum amount of energy. Now, you see in the Western world that energy for aluminum extraction comes from a variety of sources. We will talk about what happens in India. First of all, you see thermal power plants will give 23% of the energy being consumed by aluminum plants, starting from Bayer's process to smelters. But there are other sources: oil, natural gas, lignite. Nuclear energy has come into picture also. Small amount of nuclear energy is also supplying electricity to the grid, from which electricity is being drawn by aluminum plants. There are one or two other energy sources, could be wind, could be solar, it is not mentioned. But hydroelectric power is what accounts for most of the energy being consumed by aluminum industry, 62%. Why this is so should be quite clear, that while it is very expensive to build dams, but once dams are built, the water that is stored can be released at the times needed for irrigation through channels, but the water that flows down through sluice gates, once you open the gates, would also run generators that generate electricity, and generation cost is lowest when we have a hydroelectric power plant, because you do not need any raw materials there. The water that is stored has the potential energy that is converted to electrical energy through generators when the water flows down. Whereas, in thermal power plants you need raw materials, whether it is based on petroleum or natural gas, you consume input materials, and you also give out CO2. in this case nothing. You have clean pure electricity that is coming from hydropower, and besides the need for aluminum electricity is so large that it is good to have a supply from hydropower. So, in every country many aluminum plants are near hydroelectric projects. We have one near Hirakud Dam, because but then we do not have that many dams to supply electricity to our aluminum plants, and many aluminum smelters have their own captive power stations like Nalco in Bhubaneswar, Angul and Damanjodi. They have their own captive power plants. They meet their needs by generating power for themselves. If there is an excess, they can give to the grid that goes for public consumption. 50% of the hydroelectric potential of India has been exploited. Another 50% could be exploited if we could go ahead, but the possibility looks very dim, because when you go for a hydroelectric project, there are social costs. People will have to be displaced, many roads, villages, ancient monuments, scenery, they will have to be submerged. So, there is a problem associated. Then many people also say the dams have bad consequences over the long run, because it causes a drop in the fertility of the soil. Dams can cause earthquakes. So, there are all kinds of problems. I do not think India is going to have far too many dams. We do not have the scope for far too much electricity from the hydel projects, but India eventually can have more nuclear energy, which can one day supply electricity to aluminum smelters. We can also have to think of other things, alternate energy sources. Now, let me now discuss some problems and illustrations, which would perhaps throw some light on the topics I had discussed in my earlier lectures. This would be related to life cycle analysis kind of thing. Suppose that there are two kinds of motors, A and B, and their specifications are given, both of the same capacity, but one has higher conversion efficiency. Initial cost is also higher. It has a longer life, 20 years for replacement, whereas the cheaper one every 5 years it has to be replaced. Salvage value is more for this it is less. Annual maintenance is the same. Electricity cost to run also is the same. Now, operating schedule of both the motors is 8-hour day and 22 days per month, based on the life cycle cost analysis for an assured desired life of 20 years. Determine which motor is best option. This is the problem. We have to look at the life cycle analysis, because we are talking about initial cost, then we are also talking about salvage value when its life is over. Now, we solve this problem by doing a life cycle analysis. The life cycle costing is based on a consideration of all costs associated with an alternative during its entire lifetime. The following table lists the relevant costs for motor A and B for calculation of life cycle costing. Motor A, this is per year, and you get total for 20 years. Annual maintenance this, 20 years this much, operating cost annual this, 20 years this, replacement cost annual this, 20 years this, salvage value is so much, because its life is only so much. So, it has to be bought, and this will be total life cycle cost is this. For motor B, on the other hand, we annual maintenance cost is the same, operating cost is bit lower, replacement cost is lower because it lasts longer each unit, salvage value is this much, and then on the whole total life cycle analysis will find this is costing less than this. So, this is again an example of having a long term subjective horizon. It may cost initially little bit more motor B, but it on the long run it pays back. So, the life cycle costing analysis shows that motor B will cost less than motor A over the entire useful lifetime of the investment. While if one were to make a decision on motor A versus motor B based on initial cost only, then motor A will be selected. However, life cycle costing is said to be a first approximation, since no considerations is given to the cost of money. How the costing will change, that we have not considered. Now, let us come to another question. You assume that you are the energy manager of a company XYZ, and you have recently completed energy audits of several projects, and you have identified some for immediate action. You have done the audit, now you are recommending some activities for action. Preliminary engineering analysis have confirmed the technical feasibility and economic viability of the projects, that okay, the project you have in mind can be done. The following 4 projects are identified. We can think of to modify the lighting control, which will initially cost $1,000, energy saving per year will be this much, dollar saved per year will be so much as compared to the present. Install heat recovery system, that will cost something, it will save energy per year, this much of dollar saving will be per year. Temperature set back at night, that okay, you say we will put the temperature back at night, that costs nothing initially, but you will save energy per year, you will save money. Insulate building attics, the roof will insulate, it will cost some money, there will be energy saving saved per year. Now, how should you proceed to prioritize the above projects? Which one is more important, which one is less important? That is the question. How do we analyze this solution? To select the priority of the above 4 projects should be ranked based on some criterion. They can be ranked in several different ways, but we have to select the following criteria. The various criteria are least capital cost, greatest energy savings, greatest money savings, shortest simple payback, greatest energy saving per dollar invested, project which reduces electricity bills. And we give them some points, that ranking criteria, we give 1 here. Yes, now on these criteria, on project ranking, projects will be ranked based on this criteria like this. Case number 2, recovery, sorry. So, there are 4 options, 1, 2, 3, 4. Number 2 will be the worst, number 4 option will be the best in terms of the initial cost. See this insulation costs very little, so the project ranking will be like this, the best will be 3, then 1, then 4 and 2 in terms of least capital cost. If you refer to the table, it will become very clear. In terms of greatest energy saving, the ranking would be like this: best will be 2, 3 will be next best, 4 will be 1 and so on and so forth. So, we take the different criteria and find out which is worst amongst the different options and which is best in terms of this criteria. And finally, we see that if money for new project is limited, the strategy might be to implement that project which requires little or no capital cost. Hence, project 3 will get the highest priority. On the other hand, if energy supplies were short, the project 2 might be selected first. If electricity was in short supply or subject to curtailment, project 1 might be implemented first. So far, only economic criteria have been considered. Completely different answers will be obtained if the criteria be changed. For example, if the building is considered for project 4 is occupied under terms of a 4-year lease, then project 4 might be totally eliminated because money invested will not be recovered during the lease. So, you see an industry has to operate under lot of practical considerations. So, what may be the best in theory may not find a ready application. You have to fix criteria, whatever ideas are there for implementation, they have to be measured against this criteria, keeping in mind all practical considerations. Now, okay, we continue. In the XYZ plant project 1, modify light controls saved 25,000 kilowatt hour per year. However, during the second year, right after the project was implemented, a new wing was added. Suppose a new wing was added to the building. This wing caused additional lighting electricity use of 20,000 kilowatt hour. What are the cumulative project savings that are avoided after 3 years compared to the base year? Assume base year lighting energy is 250,000 kilowatt hour and escalation of price is constant at 10% per year. We are making things more difficult. I have given the calculations, I will just read out, you have to think about it, do it for yourself. The following table shows the project cost if the project 1 is not implemented. Year, energy used, energy saved, net energy cost, annual cost, everything has been given in this table. First year, second year. In 3 years, the net so much and total of this much is now the project 1 is implemented. Above table will be modified and the following table shows the result of the implementation. So, we have given all kinds of calculations, energy used, this is the base year, energy saved, net watt hour, energy cost, annual saving, which compared to base years first, second, third year, and then total of what is happening everywhere. So, in 3 years the total energy saved is 7,500 kilowatt hour and total cost is $39,670. Hence, total cost avoidance will be this. So, this is the kind of analysis industry has to do. In this example, implementation of project 1 has saved money for the first year. During the second and third year, the escalation of electricity price and increased production causing more electricity to be used resulted in an increase in the electricity bill relative to the base year. However, without the energy management project, costs would have been so much higher than they actually were. So, you think of implementation of new ideas with reference to priorities, criteria, realities, explanations, costs, everything, etc., etc., etc. Certainly, one would not think of bringing in a very expensive project which gives marginal advantages in a given period of time. Now, I am coming towards the end of this module, and I like to discuss very briefly a topic which is becoming increasingly debatable in our country, and that is electricity from nuclear reactors. Someday we hope that non-ferrous metals production will not depend so much on electricity from fossil fuels like petroleum, natural gas, and electricity from thermal power plants, which happens to be the fact of the matter today. I have given you one example where one non-ferrous industry is looking for an alternate source of energy, and that is the ferromanganese production units, Manganese Ore India Limited, with head office in Nagpur. They are getting part of their energy requirements from wind energy. So, they are first of all saving use of coal, they are not using coal for part of that their requirements, and by not using coal they have cut down on CO2 emission, and because they have cut down on CO2 emission they are getting carbon credit, and the money they have invested in setting up an alternate source of energy in terms of windmills, they are recouping within a year, year and a half, and so they gradually want to expand their involvement with wind energy. Perhaps in near future many industries would look for alternate energy sources to gain carbon credit, get financial gain, and accordingly have cleaner operation, not generate CO2. Their image will increase, but it will take time, because carbon is not used only as the form from thermal power plants producing electricity and is coming. No, carbon as coke or coal also is directly used in some industries, like blast furnace operation depends on coke as a reducing agent for iron ore reduction. Now, you cannot replace that by a form of electricity, you need coke straight away, and that is going to generate CO2 from the top. In aluminum smelters, the electrolytic process depends on use of carbon anodes, on which the oxygen discharged forms CO2 and that goes out. Now, you also need electricity to apply a voltage and pass current. That electricity we can get from an alternate source. If we are getting it thermal power plants, we can get electricity from hydel plants, we can also get from nuclear power plants, or we can get from solar energy or wind energy. But there is no substitute as of now for the carbon which is being consumed as an anode. It is a consumable anode. The oxygen is constantly eating away carbon. The cathode is not being eaten away. The cathode is finally discharged. So, we cannot think of getting rid of all the carbon, but where carbon is being used in thermal power plants, we can think of eliminating that carbon if we can go for alternate energy sources. And I have given you some data to show in many countries use of nuclear energy as well as other alternate sources of energy is growing. In France, 80% of the country's energy needs is met by nuclear energy alone. Even in many countries where there is a lot of oil and coal, say Soviet Russia or some European countries, there is substantial use of nuclear reactors. So far, China is not so much dependent on nuclear reactors, but they are also expanding their nuclear energy facility in a very big way. India also has now planned to expand nuclear energy availability substantially. I think there are some figures I will show you, but in next 20 or 30 years, they would perhaps like to make it 5 or 6 times the present what we have, which is about 4 or 5% of energy needs. Now, currently, the world has over 436 nuclear power plants. The figure is as of October 2009. This number may have gone up already, but as of October 2009, according to S.K. Jain, who is a big man in our atomic energy establishment, 436 nuclear power plants were operating with an installed capacity of 372 gigawatt. What is that unit? Sorry, I am the unit, I am not very clear about the unit. And it was supplying 16% of the electricity in world electricity consumption. 16% is coming from nuclear reactors. 35 reactors are under construction. Further, about 220 new reactor plants are planned across the world by 2030. So, by 2030, this number 436 will increase to 636 plus 35, almost 700 nuclear power plants all over the world. India plans to increase the present nuclear capacity of 4120 megawatt to 20,000, which means 5 times by 2020 and 6 to 63,000 by 2032. Now, there is another 22 years. In 22 years, we would like to increase it by almost 15 times. That is a very tall order, and by in another 10 years, we want to increase it by 5 times. So, there is not much time. In 10 years time, it will increase by 5 times, and by in 23 years time by 15 times. That is the plan. Now, Indian nuclear plants have witnessed over 300 reactor years of accident free safe operation. You know how this is calculated. 300 reactor years means if a reactor is operating for 2 years, it is 2 reactor year. So, taking into account all the reactors and their duration as to how long they have been operating, we calculate reactor year operations. Now, this is something India can claim with a lot of credit, but 300 reactor years of operation, it could be 1 reactor operating for 300 years or 10 operating for 30 years, but we have many more than 10, as you know. There has never been any accident anywhere. Now, lately there was something that happened in a reactor in the south. That was not an accident. That was a mischief created by some person. That is not an accident. So, the reactor operation that we have in India, we can consider safe. And the reactors we have also have high availability factors, means 80% of the time they were available for electricity generation. Now, this is a very important parameter, that if you invest a lot of money into creating a facility for nuclear power generation, that investment should not stay idle, which means you must be able to produce electricity all the time. In the case of nuclear power plants, you cannot do all the time. It needs maintenance, it needs many other things, but 80% of the time they are able to produce in our country. At least during the last decade, this is what is claimed. Now, worldwide, there have been three main industrial fuels. In today's world energy scenario, 43% energy consumption is met by petroleum, coal meets 36% of the world's energy needs, natural gas meet 20%. These are the three main ones. The rest are by the other sources, including nuclear energy and other things. The main emissions come from electricity and heat generation, 24.6%. The figures for others are land use change, means when you had forests, you have cut down forests. In Brazil, the Amazon forest is disappearing very rapidly. When you do that, then the forest that was absorbing CO2 is no longer there. So, that CO2 will come out. We say that that figure will be attributed to change in land use pattern. Agriculture will account for some, transportation some, industry 13%. Now, nuclear power plants do not emit any CO2. I should not say it is not associated with any CO2, because people should know that when the nuclear power plants are operated, they also consume electricity. How they consume electricity? There are all kinds of pumping of water, pumping of coolants, you have lighting, you have all kinds of things that is met by conventional electricity. So, you do need electricity, energy input in the nuclear power plants also. But someday it is maybe possible that if it is operating all the time, it generates power, generates electricity, part of which is used for utilities and services. It may be possible, but as of now you need some amount of electricity to run the nuclear power. Actually, this has been a criticism, because there have been papers giving cost of nuclear power generation. As I said, the cost of generation is the lowest for hydel power, because there are no raw materials are required. You have the water reservoir, you let the water flow down, you generate electricity. There are no inputs required. The input required, the amount of material required for nuclear power generation is very small, no doubt about that. But you need input of energy to run the utilities, run the machines, run pumps, all kinds of things. So, there has to be an input of energy there. That we, when we are talking about process fuel equivalent, we saw this in importance of looking at it holistically. So, here nuclear power plants generate electricity, surely, but they do also consume from the input end some electricity. That has to be kept in mind. And that is what I mentioned. However, the electricity consumed does imply CO2 generation elsewhere to a smaller extent. It is not very large, but to a small extent. Now, a recent issue of National Geographic, March 2009, gives the number of nuclear reactors operating in different countries as follows, and the percentage of countries' present needs, energy need met is also given in brackets. Some of these figures may be contested, at least the figure for India. I will tell you why. This is the very important country's need. France with 59 nuclear reactors meets 77% of the total energy need of the country. It is a remarkable example. And I told you earlier, France does not have coal, does not have petroleum, does not have natural gas. So, they took long ago, they took strides to be a nuclear power, and they have done that. No other country can come anywhere near that. But look at South Korea, which started late. 22 nuclear reactors are meeting 55% of the country's needs. Japan, we hardly talk about this, but Japan also has 55 nuclear reactors. 28% of countries' energy need is coming from nuclear reactors. Now, obviously, the capacities of these nuclear reactors may not all be the same. That is why perhaps even if we have 17 nuclear reactors, we may not be producing as much electrical energy as 17 reactors in those countries are producing, but that is a different matter. In the US, which is flushed with oil and coal, it's rich. They have kept all their coal practically unutilized reserves. They are trying to get it from the Middle East. They run 104 nuclear reactors, getting 19% of their country's needs. And these are all very recent figures, March 2009. In Russia, also, Russia is a country which exports the largest amount of petroleum. They are even ahead of Saudi Arabia. They are so rich in oil, but they think there is wisdom in going for nuclear reactors. So, they have 31 reactors giving 16% of the country's needs. Russia is unfortunately a country which has given a scare, because they had a Chernobyl disaster, which was a very serious accident. And in that area, people are still suffering, and they may suffer for generations. Now, God forbid if something like that happens in our country. You should understand why one is a bit hesitant about nuclear reactors in India. We are not very good in maintenance of any kind. We are very good in creating things, but we are very poor in maintenance. You look at any building, especially buildings created by a government, beautiful buildings we make, then we do not know how to maintain. This is not so in Western world, where whatever they create, they maintain beautifully, and they look new, and sometimes they look improves with time, because they are tuned towards maintenance requirements. That culture is not very good in India, and that is why many people tell that India has to be very cautious about nuclear plants, because we have to first train ourselves in maintenance. It is not that we cannot do that. Today, you go to any 5-star hotel in India, I am sure you must be, and go to a government run guest house. or a government run hotel, you will see the stark difference. How the maintenance is done in 5-star hotels owned by private hands, because there is different kind of work ethics, discipline and command authority change operates. We have to bring in that kind of culture in nuclear plants, so that they are maintained spick and span. If something has to be cleaned, it has to be cleaned every day. If something has to be tightened, screws, they have to be checked every day. They are doing that in India. So, we have even in our government setup institutions which are operating in a different level of maintenance, but we have to ensure that. Now, coming back to this, in UK 19 reactors are giving 15% of energy needs countries. We have a good number 17 reactors in India, but it is meeting only 3% of country's needs. This figure quoted in National Geographic may be low. I have heard a figure of 4. Why is it so low? Obviously, it could be because of 2 reasons. Maybe the reactor capacities are low, or secondly, it could be because our total energy requirement is so large. Now, China with 11 reactors was behind India, and in terms of supply of energy needs only 2%, but things are changing. They are going for a big expansion pump. Now, here I have mentioned that. So, the number of reactors in India is actually more than as mentioned earlier, and they are meeting more than 4% of country's energy needs. Now, with that I complete module 9. Now, I tell you what happens now. I completed discussions for the entire course, starting with general principles of extraction, refining, then extraction of specific metals from sulfides, oxides, halides, talked about noble metals, talked about secondary metals, talked about energy and environment related issues. Now, I have requested a friend of mine whose name is Mr. L. Pugajendi to deliver 2 special lectures to you. Mr. Pugajendi, whom we normally just call as Pug, is a very popular person, good speaker. He is Executive Director of India Lead Zinc Development Association. He is very knowledgeable in the area of non-ferrous metals, and he was President of the Indian Institute of Metals last year. He is going to deliver 2 lectures on non-ferrous metals in India, unleashing its true potential. He will give an overview. He will tell you why it is important to study non-ferrous extraction metallurgy and what is its role in the economy of the country in the coming years. After those 2 lectures, I will take 2 lectures to review the entire course from the beginning till whatever has been done so far. Thank you.